Hello, welcome to the video on work, and we're going to go into a little bit more detail about this idea because it's something we see really often in physics and it's very useful, and some people sometimes find it a little bit confusing, so we'll talk about it here in a bit of detail. The other way that normally this is called, you'll see it very often written as work done like that. So let's see, what is work done? A good definition that I've seen is this one here. So I'm going to write it all out so you can copy it. Work is defined as the product of the force acting on an object, product of the force, and the displacement moved by the force. And the important part also is that it has to be in a straight line along through, in a straight line along through where the force acts. Okay, so hopefully, wow, that was a bit, hopefully this makes sense. Force acts. I'm being clumsy with my pen today, apologies for that. So work is defined as the product of the force and the displacement moved by the force in a straight line along through where the force acts. So in other words, we can say that the work done is equal to the force times the displacement in the direction of the force This can also be thought about in the other way around. It can also be the force in the direction of the displacement times the displacement. They are really the same thing, and I'll go into what I mean with that in a second. And as an equation, then we would write it as so. I like using the E for energy because this reminds me that work done is really made in joule. It's measured in joules, and it's a type of energy. So I normally write it like this: the work done is an energy is equal to the force times the change in displacement. So it's important to know that these have to be in the same direction. So I'll talk a bit about that now. And just before that, I also want to mention that. So when does this happen? When is work done? Work is done when the point at which the force is acting actually moves. So you can say that the work is done when the point of application of the force actually moves. Force moves, right? So if I have a block here and I have a force and it's being applied there, and this point there then moves, then the distance, the change in displacement of that point, this thing here, will be the delta S, and therefore work is being done. So work is done whenever the point of application of the force is moved. Hopefully that makes sense. And what I was talking about here with the direction of the force and all of that, this is what I meant really. You can have a situation where you have a block and it's on a table, and we're gonna push the block like this. All forces are always red, obviously. No, they're not. Don't quote me on that. I'm just being silly. And this is a force, and it's going to act on this block there, and if the block's gonna then move, let's say it moves a distance delta S, then the work done would be very easy to calculate. I could just say EW is equal to F delta S from there. And so if the force was, for example, 8 newtons and delta S was 2 meters, then my energy or my energy increase, or my work done in joules, the amount of work done, would be the 8 newtons here, 8 newtons times delta S, which is 2 meters. So that would be 16, and the unit of work is joules. So that would be 16 joules would be the amount of work done on the system. So that's very easy to calculate. But sometimes we have situations where it looks a little bit more tricky. So for example, you could have a trolley like this and somebody doing work on somebody putting a force on it or doing work on the trolley, and perhaps the force applied would be like this. It would be at an angle theta to the horizontal, but the movement of the trolley is along the floor, right? So this would be my delta S. So what would happen here? Let's see. Just want to use the same colors, and that force should really be red, because I was using red for forces, but doesn't really matter, as I'm sure you realize. So we have this force at this angle theta acting on this green trolley, and the distance is in that direction, but the force is at a different angle. So then our formula, we can't just use F delta S, because we need to go here and understand the meaning of this statement here, which says that it's going to be in the direction of the force, right? In the direction of the force, the displacement in the direction of the force. So the displacement in the direction of the force means that we need to get the force, we need to find out how much of this force actually is going along the same direction as the displacement, and then we will know what force acts along that direction, and we can then do our calculation. But right now they're not in the same direction, so we can't really do it. So if this was, to put an example, if this was 20 degrees and this here was 100 newtons and the displacement was 30 meters, then our equation would be the work done is equal to the force times delta S, but the force in this case would be the full force, the force component along that direction, which is Fx. So if we take our F horizontal, so if we take that to be a horizontal direction, there would be F horizontal times delta S. And in that case, F horizontal would be equal to the full F here times cos, because this is the adjacent, right? That would be the hypotenuse. This is the opposite. F cos theta. So we would have F cos theta times delta S. Hopefully that makes sense. And so F is 100, the theta was 20, and delta S was 30 meters, because it's going in that direction, so we use the full 30. So then the work done we can calculate easily with a calculator. So I'm going to do just quickly 100 times cos of 20 times 30. That's 2,819. 2,819 joules. To three significant figures, that would be 2,820 joules. If we wanted to leave it to three significant figures. And so that's the amount of work that we've done on the object. So we've always got to use the force that goes along the same direction. And we also have to know about force displacement graphs. So if I draw a graph here, and this is the amount of force that I'm putting on an object, and this is or applying on an object, and this is the displacement, and that's in meters, this is in newtons, then say my graph looked something like this, because I'm probably stretching something, and so it starts a bit straight and then it sort of goes like that. Then if I wanted to know what the work done by that force throughout this displacement on an object, then all I need to do, let's say that here I was at a displacement of and call it S1, and here I was at another displacement and I call it S2. Then the force at which this happens, F1, and the force at which that happens was F2. Then this area here, all the area under the graph, all of this, right? It came out here a little bit, but ignore that part. Wanted just to be precise. Rub it off. And that area there, all of that area, would give us the work done. So this would be, that area would be the work done. So can really we can write it as a rule, really, and remember that. So the work done is equal to the area under a force displacement graph. Okay, and so this could be either having a block and putting a force in it, and this would be the displacement and that would be the force. That's what we could calculate the work done. Or it could be just a material that we're stretching, and that's the original length, and then we stretch it this much, and then this is the displacement away from its natural length, and this is the force that we're putting onto it. Then the area under the graph that we get would also give us the work done. And in this case, if it's a hook material, it would be a straight line, and then we could calculate this area, and we'll talk about that a little bit later, but we can use it for that circumstance also. So just a quick summary before we finish the video. So we wanted to introduce the idea of work done, and we said that it is defined as the product of the force and the displacement moved by the force in a straight line along through where the force acts. So hopefully that in itself is a good enough definition, and you can see why this is here the case, that the force needs to be in the same direction as the displacement. And we did a few calculations, one of them was straightforward and another one at an angle, and then we've talked about this idea where the work done is calculated or is represented also by the work done, by the area under the force and displacement graphs. So we'll use this idea later to calculate the formula for amount of elastic potential energy using this idea here. So thanks for listening, and see you in the next video.